Today's lesson, double angle formula, and it is such a rich lesson, but I gotta tell you, there are some very, very difficult parts to this. And I've tried to lay the note out very, very carefully to really guide you through all the little pitfalls that can come up in this section. So, it starts with some stuff on development of the double angle formula, of where they come from. I don't know if I encourage reading that first. They start off with this stuff here, which is a good reading for later. They're using the sine addition formula, and all they do in the sine addition formula is replace A and B with the same angle. They're both equal to each other, and they get what's called a double angle formula. What do you need out of here? Double angle formula. If you've got sine 2x, you can turn it into 2 sine x cos x. So if you've got a 2 inside, the way that develops out is that it pops out front, but you get sine and cos back out of it. That's the way the angles work. That's the way the whole thing works. It's not a distribution thing. It's just the way trig works. How does that thing get used? There's an example there of how it gets used. I don't want you to read that now. Just use it as another example. I'm going to do one like this later on, one of my own, that is really, really focused on your homework. But you can come back and look at this one a little bit later because it sort of streamlines the process a little bit. So after doing some of the homework, you can come and check out that one. Then they do development of the cosine double angle formulae. There's 3 of them, 3 double cosine angle formula, and they're right there. And all they do is take the cosine addition formula from last lesson, and they put in the same angle. They say, okay, A and B are both x, and so you get these double angle formula. Again, this course, you're not responsible for those proofs, just of using them. And you're like, well, how do I use them? No problem. I'm going to get to that. And when we get to what I called a little later, I call them awesome double angle problems. Those are the problems that you're responsible for, is using these double angle formulas. So I'll talk more and more about how to use these things as I get down there. Okay, and then they really take it up a notch, and they really show you what cos double angle formulas can be used for. And then they do, and I'm going to do a problem just like this later. They do the real application. I would say this is the very best problem of the section. I'm going to do one just like that coming up, no problem. I'm going to do one a lot like example 2. I'm going to do examples like this. So these are, you can think of these examples up here as bonus examples. If the examples I do on the screen when you go to do the homework aren't enough, if you look and go, I don't know, I sort of get it, but they're not helping me quite enough, you might want to come back and look at these examples. But I'm telling you, I'm doing most of this stuff. Then they develop the double angle formula for tan, and they do an example as well. Okay? The end result of all that is, by the time you're done all in there, and I'm going to see if this will just move down, because I really wanted that for this part of the lesson. Get my cursors out. Allow me to pull that down onto the next screen there. There it goes. Perfect. That's where I wanted that to explain these examples here. Okay. And I see my thetas are missing. So I'll fill those in. All those symbols from the equations are missing. But I'll fill those in as I go. They should be in your note. Okay. First example I want to talk about. Make that a little smaller right there. There we go. And in your note, I hope it says, express cos squared 2 theta minus sine squared 2 theta as a single trigonometric ratio. We got some flavor of this in last section about what they're talking about there. What they're talking about is using these double angle formula right here, which I've now given you, that are all sitting right there. And what they want to do is get this down to one single trig ratio. See, right now it's 2 different trig ratios. There's coses in there and there's sines in there. They want to get it down to one trig ratio. Now, if you look through the list and see the pattern here, it says cos squared minus sine squared. And if you look through your double angle formula, you see I have that right there. I'm going to highlight it, this formula right here. There it is, cos squared minus sine squared. Now, it's on the right side of the formula, so I want to go right to left this time. So I'm going to write that exact formula. I'm going to try and write it right underneath here. Cos squared x minus sine squared x And apparently that comes out to cos 2x. All I've done is taken that exact formula and written the right side first and the left side after that. So in this particular question, though, it's not cos squared x minus sine squared x. It's cos squared 2 theta minus sine squared 2 theta. So every time I see x, they want me to write 2 theta. So I'm writing cos squared of 2 theta minus sine squared of 2 theta. And that apparently is going to come out to cos of 2x. Now this is where the thinking comes in. I replaced x with 2 theta on the left side of that formula. So when I come to the right side, I've got to replace x with 2 theta. If you want, I'm going to go let x equals 2 theta. I'm just going to write that exact formula, the double angle formula, but I'm going to replace it, all the x's, with 2 theta. And so then what I get here is cosine of 4 theta. That's what they wanted, a single trig ratio. See, just cos now, not coses and sines all in one, just coses. Interesting application. Not clear where all this is going, but we will continue on. That's what they mean when they say a single trig ratio, is look at the double angle formula and see if you can go right to left, because on the left, it's always a single trig ratio, always just a sine, just a cos, just a tan. This one, it says use a double angle formula to rewrite cos 4 theta in terms of the angle theta. So now they want cos 4 theta. So what I'm going to start with is, and again, it may seem a little mysterious why I chose to start with this one, but there's another version of cos of 2x, and you can use any one you want. There is no one you have to use for a question like this. I'm just going to use this one because it's slightly different than the one I just did, is I'm going to write down the formula cos of 2x equals 2 cos squared x minus 1. I'm going to choose that version of the formula to use, and it's just a choice I made in this particular question. I could have used the other ones. But they want to rewrite cos 4 theta. So it can't be 2x on the left side. I need it to say cosine of 4 theta. So what I'm going to do is I'm going to go let x be 2 theta. And the reason I chose 2 theta is when I put in x as 2 theta, I get cos of 4 theta there, because 2 times 2 theta is 4 theta. And that's what they wanted. So that's why I chose x equals 2 theta. It wasn't some random choice. I just looked and went, what do I need this to come out to? They want an expression for cos 4 theta. To do that, the x is going to have to be 2 theta. And so what I have on the left side, right side, I'm going to try and do it quickly to keep that in your head, is I just said, oh, x is going to be 2 theta. And I've done a great job of rewriting. And one of the homework questions asks you to do this. It just says to rewrite it, the cos 4 theta or the sine 4 theta. And I've done that. I've rewrote it as a different set of trig ratios. But this one says I made it a little more difficult here to really try and take things up a notch here. And I said, no, get it down to angle theta. See, this one right now says cos 2 theta, and they want it down all the way to theta. So I'm going to do an extra line here to get ready for that, is I'm going to write 2 cosine 2 theta. And this is really what we mean when we say cos squared 2 theta. We really mean take cos 2 theta and square it. I hope you've seen that before. It's just a shortcut we use in math because we find it easier to write when we have expressions like sine and cos and later logs. We find it easier to write the squared over top like that. But this is what we mean, and sometimes we have to write it like that. That's a great move, to write it like that, so that we go, okay, what's really going on here? I'm taking cos of 2 theta, and I'm squaring it. So now I'm going to take this cos of 2 theta I got, and I'm going to replace it with the same thing I just did with cos 2x again. I'm going to use this formula and say, okay, I'm going to replace cos 2 theta with what I've got for my cosine double angle formula, which is 2 cos squared theta minus 1. I've just replaced that. Okay, highlight both of those. I've just replaced cos 2 theta. Now I'm unhappy with that. I really want that to look different than the previous one. So let me get rid of that. And I'm going to highlight it in a slightly different color to show the different thing I did there. I took cos 2 theta and I replaced it with 2 cos squared theta minus 1. Now, why did I do that? Well, now I've done what they asked. They said get it down to in terms of angle theta, and that's what that expression is. It's a big mess, but it only has thetas in it. It doesn't have 2 thetas. It doesn't have 4 thetas. Now, it didn't ask me to simplify, but I really should. I should take this two sets of brackets, this squared, and set it into two sets of brackets here, and do that difficult expansion there. When I expand out those brackets, I get 4 cosine power of 4 theta. And then, let's see, I get minus 2 cos squared theta, minus 2 cos squared theta, and then a plus 1 in the brackets, still a minus 1 outside the brackets. 8 cosine to the power of 4 theta, minus 4 cosine power 2 theta, minus another 4 cosine power 2 theta, a plus 2 and a minus 1. Collect up like terms. And this is really starting to prep for trig identities. Trig identities are such an important aspect of being able to do trig and do massive trigonometry problems. We're not really getting carried away with that here. We're just starting to poke towards the algebraic side of trig here. Okay, lots going on there, but the big part of that example is being able to see what they were asking for. There's another example like that higher up in this lesson that I glossed over that you can look back at if you need more examples like that. But this is a lot like what the homework asks you to do this one. Okay, next question. This one's a lot like last day's problems. It says if sine theta is negative 5 over 13 and cos theta is 3 pi over 2, and those little symbols didn't come out in this version of the lesson, find sine theta, cos theta, and tan theta. Now, in preparation to do sine theta 2, cos theta, and tan 2 theta, I'm going to draw what they've asked here. Is they said, whoops, that's not what the lesson said. It didn't say cos theta. What it said was pi is less than or equal to theta is less than or equal to 3 pi over 2. If you print out your version of the note, I hope it comes out like that. If your version of the note doesn't say that, that's what the question's meant to say there. Okay, so now I'm going to try to draw this angle theta and understand what the heck is going on here with theta. And that's going to help me answer the question. They said sine theta is negative 5 over 13, but they told me what quadrant to look for theta in. Theta is between pi and 3 pi over 2, so it's in this quadrant here, and I'm going to draw it fairly big so you can see what's going on here. And the sides in this, it's got opposite negative 5, and it's got hypotenuse 13. And I'm going to get ready for this question because we saw questions like this in the last section where for parts of the question, we're going to need this extra side here. And I'm going to go, okay, b squared equals 13 squared minus 5 squared. B squared equals 144, so I get b equals 12. In this case, it's really negative 12. Because but I'm going to handle all that with the cast rule. I put it on the picture there, but the cast rule really answers all that. This is a tan positive quadrant. Only tan will come out positive in this quadrant. Sines and cosines will come out to be negative. Okay, all that work, you may not do that work first, to be honest. When you first see those questions, you might not know you need to do all that stuff. That might come later. You might have gone ahead and said, well, I'm going to go after sine of 2 theta. And how do I do sine of 2 theta? Well, that's what the double angle formulas are for. You go up here and say sine of 2 theta is, let's see, up in the top right there, 2 sine x cos x. So I need 2 sine theta cos theta. Now sine theta, they already gave me in the question. They told me that was negative 5 over 13. But cos theta, I wouldn't be able to do if I hadn't done that work with the Pythagorean theorem that you saw above there. I'd be now... it might be a mystery to me, so I might have to do that work now, depending on how you did the question. But then I get, okay, adjacent over hypotenuse. And just like that, I've got everything I need to find sine of 2 theta, which is 2 sine theta cos theta. Just do some multiplying together here. What do I get? 60 over 169. Multiply that all by 2, I get 120 over 169. Exactly, not some decimal answer. Okay, then they wanted what? Cos of 2 theta. And you got many choices here of how to use it. I really like this version, 2 cos squared theta minus 1. I find that the easiest one to work with. But in other situations, you might want to use the other versions. There's 3 different versions of cos 2x. You say to yourself, why is there 3 different versions? Okay, well now that would be the time to go back and look at this part of the lesson right up here, which we glossed over because you're not really responsible for it in this course, but they do it right here. This is where they get the cos double angle formula. So you can go back and check that out now if you're interested. Don't really need it for this course. We just have to use them. So cos 2 theta equals 2 cos squared theta minus 1. We found out a second ago that cos theta is adjacent over hypotenuse. It's negative because it's in a tan positive quadrant. And the rest of it's just simplifying the numbers. Here I get 144 over 169. And I get 288 over 169. I'm going to need this with a common denominator, so I put it over 169. And I get 119 over 169. Very close to the sine 2 theta answer, weirdly here. That doesn't have to happen all the time, but it did here. And the last one, tan 2 theta. Only one choice for tan formula. If you look up here, 2 tan theta over 1 minus tan squared theta. So I put in tan theta, which is opposite over adjacent. So I think it's 5 over 13, positive now, because it's negative over a negative, or because it's in the tan positive quadrant. And then, 5 over 12. I don't know. I looked at that, and I saw the 12, but then I said 13 for some reason. 5 over 12. Yeah. 2 tan theta over 1 minus tan theta squared. And the rest of it is just working with the fractions here. So on the top, I get 10 twelfths. On the bottom, I get 1 minus 25 over 144. Let's see, 10 over 12 over, 144 over 144. Subtract another 25. What do I get? 119 over 144. You can handle these fractions in different ways. I find it easier to write them out separately like this. And I get 10 over 12 times 144 over 19. Let's see, that 144 over 12 is going to reduce nicely to 12 and 1. So I get 120 over 119. Incidentally, I could have used sine and cos here. I could have gone tan equals sine over cos, and I could have gone 120 over 169 over 119 over 169 and got to that answer directly. So a little trick there if you want. I use the formula to really illustrate how that works with tan. Okay, so sort of similar to questions you saw in the last section. It's just that you got to use different formula this time. These formula right here, these double angle formula, which are on your trig toolbox. If you look on your trig toolbox, they're all right there, ready to rock and roll. So those 3 questions are really, they're way more difficult than last section, but they should seem sort of familiar to last section. They sort of play out in a similar way. This question is new. It says find cos of pi over 8 exactly, and this is a very difficult question to even get the first line written down. The problem is pi over 8 is not in a special triangle. If I draw special triangles, I don't get pi over 8. I get pi over 3, I get pi over 4, I get pi over 6, and none of those things are pi over 8. And there is no fancy way, unlike 12ths and 24ths, that sometimes you can make to work with the other angles with adding or subtracting. There's no way to come up with pi over 8 by adding or subtracting things in the special triangles. So, 2 unbelievably important things to realize if you're going to have any chance at this question. If you take pi over 8 and double it, you get pi over 4. So this is a doubling question. If we can double that angle, then we can get the answer. So that's why it's a double angle formula question. Now, here's the other weird part. If we're going to double the angle, we need to use one of these formulas in reverse. That is, we're going to take this pi over 8 and we're going to put it into the right side of one of these equations. Now, that's difficult to understand. If I put it in the left side, when I come over to the right side, it's going to become half of what it was. See, the 2x's become x's. I want the x's to become 2x's. I want my x, pi over 8, to get doubled. And to do that, I need to put the pi over 8 into the right side of one of these equations. Now, which one? Well, definitely not this. This is too complicated. It's got sines and coses. Not this. It's got sines and coses. Not this. It's got tans in it. It's got multiple versions of tan in there. The simplest one to work on is the one I've already got highlighted here. And the reason I like that one is because I'm trying to find cosine of pi over 8. If I was trying to find sine of pi over 8, I might use this one here. So that's one of the homework questions here. Well, all of that may seem like I'm just making up stuff. I'm just talking out loud until you actually see it happen. Let me just write down that formula to try and convince you how good it is. It says cos 2x equals 2 cos squared x minus 1. And again, if you're completely lost on everything I said just now, it might become clear when I write down this line right here. Let x equal pi over 8. And again, a mysterious choice. You're like, well, why did you do that? It could be when I write the next line, you go, I see why you did that now. I understand everything you just said. Or you have a better understanding of it. You might want to go back and watch this video from the start of this question after I write this line. By let x equal pi over 8, on this side, I get 2 cos squared pi over 8 minus 1. There's what they want, the cos of pi over 8. That's what they're after there. So let me just highlight the cos of pi over 8. They want this, cos of pi over 8. Now I've got that in my question, cos of pi over 8. That's one reason why I chose to do what I did. The other reason I chose to do what I did is now this side becomes cos of 2 times pi over 8. Let me just go one more step. 2 times pi over 8 is 2 pi over 8, which reduces to pi over 4. Why is that so good? Well, cos of pi over 4 is right there in the special triangle. That's why I did everything I did in the order I did it. I put the pi over 8 in the right-hand side, so it would double on the left side. And when it doubled, it became something that was in the special triangles. That's what I will call a giant step in doing this question. We're not done yet, but now we've at least written down a formula that we can use to get this answer. What I mean by that is we can find cos of pi over 4. We know that's 1 over root 2. And I'm going to rationalize that denominator right off the hop. I multiply top and bottom both by root 2. Now, the rest of this question actually is just about isolating that cos of pi over 8. Cos of pi over 8 is in this question now. I can see it sitting there, and I just have to solve for it. I just have to move things around to figure out what cos of pi over 8 is. For instance, I'm going to take this negative 1. I'm going to move it over here. And I'm going to get a common denominator there so that I can add those two fractions together. That becomes root 2 plus 2 over 2. Then I'm going to take this multiplier 2 that's out front. I'm going to divide everything by 2. And when we say divide by 2, what we mean is multiply by the inverse. And so I get root 2 plus 2 all over 4. And finally, square root. Now I know what cos of pi over 8 is. A couple of extra little details. I really can actually go one step farther here. I can write it like this. Because I can take the square root of that bottom part. And I don't know why I wrote an equal sign there. One other thing. We did a square root there, but we didn't do plus and minus. And the reason we didn't do plus and minus is because cos of pi over 8 is in the first quadrant. We know it's a first quadrant angle. Pi over 8, if pi is all the way over there, pi over 8's in here somewhere. So we know it's in the all positive quadrant. So we know it's not plus minus. It's just plus. So I didn't ignore that plus minus thing. I just knew which answer I wanted here for cos of pi over 8. If it had been cosine of some different angle, then maybe I would have wanted the negative answer here. So I'm actually using the cast rule there to make a decision on that positive. Well, if that's not one of the craziest questions you've seen ever, I don't know what is. That is a wild, wild question. There's a lot to think out to even get the question started. In this course, we only ask you to repeat that. We give you other angles to try that with. So when you get to an angle that would be doubling would be a great move. A doubling would get you to a special triangle. Then try this. Watch this example again and try to walk one through. Maybe even now, take a moment and write down cos of pi over 8 and see how much of it you can do yourself and walk through those steps in preparation for what's in that homework. Okay, one of the toughest sections of the course, folks. There's some tough examples, and I hope I've given you 4 nice examples here, and then there's 3 good examples up here. Let me circle them for you that are similar to the ones I've just shown. Example 1, example 2, and example 3 with full solutions there. They have slightly different steps than mine, slightly different layout than mine, but very, very similar examples that can help you. Really attack this stuff, because the rest of this chapter does get a little bit better after this, but this is one